mechanical engineering in the information age is designed to look at the role of information in mechanical engineering. Now, my background is in physics. When I came here, I didn't know anything about mechanical engineering, but I knew a bit about information. And over the past 5 years, I've been amazed at the extent at which problems in information and information processing permeate the whole fabric of mechanical engineering. You know, you buy a car, it's got 30 microprocessors in it, right? That's a lot of microprocessors. They all have to talk to each other in the right way, or else your car doesn't run properly. Similarly, I've had a great appreciation as my job, I try to build extremely small, powerful computers. And I've got a much greater appreciation for the extent to which mechanical engineering has contributed to the information revolution. Many of the primary breakthroughs that allow us to have the computer revolution at all were mechanical breakthroughs. Breakthroughs in materials, breakthroughs in processing, breakthroughs in manufacturing. So this conference is here in recognition of this fact and to discuss what's happened and what we're going to do about it. My name is Seth Lloyd. I am a member of a triumvirate that Professor Nam Su set up, a 3-man group. My other organizers are Sunny Su and Sanjay Sarma. I should say that the triumvirate was an ancient Roman custom. And Sanjay Sarma is the Julius Caesar of our triumvirate. He is the one who really did all the organization for this. Sunny and I are just like the Pompey and the Crassus. Okay. So, to keep us on schedule, I'd like to introduce our first speaker, Nam Su, the head of the Department of Mechanical Engineering. He's the Cross Professor of Mechanical Engineering at MIT. Nam Su.
Thank you. Can you hear me if I talk from here? I guess so. Well, certainly I'd like to welcome all of you to MIT, and I'd like to thank our colleagues for organizing this. Seth Lloyd said he didn't know anything about mechanical engineering. At the time we interviewed him for a job, that's not what he said. We hired him because he told us he knew a lot about mechanical engineering. But certainly it has been a pleasure to work with my colleagues in the information area. Today you'll be hearing from very distinguished speakers, and especially the keynote speakers today and the luncheon speaker, dinner speaker. These 3 people, although they may not realize it, they had a profound influence the way we developed information technology. In fact, they had a profound influence on me, the way that I think about information. And indeed, many of the things we have done have been affected by their thinking, indirectly and directly. So I'm looking forward to their talk today, and I hope you'll enjoy their presentation as well. May I share the next slide? One of the reasons we decided that perhaps we should have this conference is that we should exchange information as to what all of our sister institutions are doing in the field of information technology. And also we want to tell you about what we are doing. And also it's no big secret as to what we have in mind. I hope that some of our sister institutions that do not have strong programs in information area will start programs and hire our PhDs. We are producing a lot of PhDs, and hopefully you'll hire them, and that in turn will make room for our future students in our programs and so forth. And I guess one of the important issues is why IT in mechanical engineering. In fact, within our own department, we have had a great deal of debate on this issue. In fact, the first committee we formed in our department to look at this issue came back with a report that says we shouldn't do anything in this field. So we formed another committee. Headed by Harry Asada, and that committee came back and said, yes, we should do something. So we said, gee, now we have unanimous support for the idea. So this is how we justified getting into this business. And so since then, we did a number of different things. I want to review with you briefly what it is that we are trying to do. It all has to do with our educational goal here in mechanical engineering, and I'm sure it's true of many other departments at MIT. Our job is to produce future leaders. So we ask ourselves what our future leaders need to know to lead industry, to be a leader in engineering, academia, and so on and so forth. So our conclusion was that indeed, for future leaders, it's almost indispensable not to teach our students something about information technology. We have to give them the background information, knowledge required so that they can become leaders. Very few things are purely mechanical anymore. And indeed, the whole idea that the mechanical things consist of geometry, I think is ancient, and we have to depart from that. And so we decided to go into this. So what we have decided to do is in addition to, it's not in lieu of or in place of, but in addition to the traditional mechanical engineering subjects, we have to teach our students something about information technology and also biology. So we decided that one of the major goals of a ME department is to transform. Some of my colleagues think that this use of the word transform is too strong a word, but really to transform, in my opinion, to transform mechanical engineering from a discipline that has been based primarily on physics into one that's based on physics, information, biology, while maintaining strong foundation in design. If you look at this, you can see that the word physics and biology are related to natural phenomena, but word like information is really related to synthesis or artificial science or however related. It turns out that that's what engineering is all about in some ways, because we do design, and design really is artificial science or synthesis. So in 1995, we created Double-Off Laboratory for Information Science and Technology under the leadership of Harry Asada as director and Ian Hunter as a co-director of the laboratory. So they are the ones who worked very hard to create a research base, create educational programs. So all the credit goes to those people plus other colleagues who are in the Double-Off Lab. So what we have done is we added very outstanding faculty members, and many of these colleagues have disciplinary backgrounds other than mechanical engineering. Seth Lloyd is physicist, and Sunny Su is electrical engineer, and you'll hear about what they are doing. And Sanjay Sama is mechanical engineer. So you can see that the new intellectual frontiers these people are creating by working together is really what's making information technology possible within the Department of Mechanical Engineering here at MIT. So you'll hear about new subjects they are creating, and they have vigorous research programs and so forth. One of the things that I thought I should tell you a little bit about our philosophy about research, and I keep talking about this with anyone I can talk to, is that if you plot on a horizontal axis research spectrum, and then along this axis, if you plot impact, it's hard to see, I mean, the research activity level, it's hard to see. This slide is not very good. So this is a research spectrum. So we go from very basic research or fundamental research. You can define any way you like. And this is technology innovation. And this is activity level along this axis. And typical distribution is something like that. Most of the professors and large number of researchers are in this middle area. They spend, I think 90% of our colleagues in universities are in this area. But if you look at the impact made by this kind of research, the curve is just an inverse. So I say at MIT, we should concentrate at this end and at that end of the research spectrum. And I say we shouldn't really care whether someone is at this end or that end, rather than argue about what is engineering science and so on and so forth. There are all sorts of basic research one can do, and there's all kinds of technology innovation one can do. Some people are able to do both. Some people want to stay at this end or the other end. And I said, that's fine. And then let the middle ground be left to someone else. So I guess one of the things we need to talk about, what is information? Information can be defined in many different ways. You know, to prepare the slides, I looked up Webster's dictionary, and there's many, many definitions, right? So for the purpose of what I'm going to say in a few minutes, I say information is a knowledge that must be added to achieve certain functional requirements. Okay? So information can be measured in terms of probability of success in terms of achieving those functional requirements. Then what is information technology? If that's information, what is information technology that we're concerned about here? It has to do with generation of information, storage of information, transmission of information, codification. Codification should be down there, somehow up there. Algorithms, comprehension of information, deciphering information you transmit, machines that produce information, devices that deal with information, and equipment for doing all of the above. Okay? So that's information technology, very broad. One of the issues some of our colleagues raised within our own department when we talked about this, what is information? There is no such thing as information. But to me, all of these are included within the term information technology, or IT. May I show next? I think there are two reasons why mechanical engineers must get involved with information technology. And this, again, is influenced a great deal by my association with Torossian, Neil Pappalardo, and Alex Sobolov. You'll be hearing from them later on. Mechanical things are getting much, much smaller. I didn't realize how small they are getting until I joined Popkin in the area of lithography, and it's really amazing. Literally, in the cross-section of our hair, we can put in 1,000 lines, and there's a lot of electric circuits on the cross-section of our hair. And we can do this because of mechanical engineering technology, because of optics, and because of all these things. And as a result of this, we started looking for optics people, and I think today, if I may say so, our department has the strongest optics, perhaps, group within MIT, if not in the country as a whole. May I show next slide? The other thing that's happening is at the opposite end of the spectrum. Mechanical engineering is becoming very highly distributed. Factories are located all over. Design is done globally. You have to exchange information, in large number of people in distant places got to work together to create the same final output. And that cannot be done without our understanding of networking, without our understanding of how design should be done in a systematic fashion, and so forth. It turns out that mechanical engineers always dealt with information. We never called it information. We are always in the area of design and manufacturing. Essentially, these two fields manipulate information to create artifacts. And that's the business we have been in, and we just did not call them information. So I'll give you a short, very simple example of how we evolved. On my own research, we evolved asking some very basic questions, how one goes about designing simple things to large complex systems, and how it resulted in a complete new technology for creating software, as well as many other things. So it turns out that in XML design, there are only two axioms. One is called independency axiom. The other one is called information axiom. And it requires that the functional requirements must be independent throughout the design process. And we have to define what we mean functional requirements and so forth. But essentially, that's one of the axioms. The other axiom says information content must be minimized during the entire design process. Very simple statement. And from these, we have a large number of theorems, corollaries, what have you, which can be used by students in coming out with good design. So based on this kind of thinking, we in fact create a very complicated commercial software. And I'd like to just tell you a little bit about the process by which one goes about creating this kind of software. May I show you next slide? So in XML design, we talk about going from mapping from domain to domain. First of all, we assume that there are 4 domains: customer domain, functional domain, physical domain, process domain. And then as a next step, we say you have to map it between the domains. And when you map between the domains, you have to maintain independence of functional requirements. And that is, you have to maintain from what it is that you're trying to achieve to be independent from other things that you want to achieve. And then after that, you have to zigzag and create a hierarchy And you cannot decompose something by staying in one of the domains. You have to zigzag, so that the only way you can decompose is zigzag it. And then you can create hierarchical structure in each domain. And then independency axiom tells you which are the good designs, which are the bad designs. And then it tells you a procedure by which you have to follow your design to be able to satisfy these axioms. So if applying this idea to a software, it looks like this. Applying this to software, it's sort of like a V model. We're going from functional domain to design domain, and that's this part of the leg. Going from design domain to process domain is this part of the leg in software design. And essentially, we design along this leg first, and then this is, typically, it's very equivalent to object-oriented programming. But by doing this, we create object-oriented program, the structure of it, without any human intervention. So in fact, you can think of creating a software without much human intervention. Measure next. So as a result of this kind of thinking, as you design it, you have a matrix. Sorry that you cannot see this, but these are functional requirements, and this could be the design parameters. In this case, we are showing design parameters versus process variables, but you can plot the same thing where this is functional requirement and that's the design parameters. These are what people might call object-oriented programming. This is what you call object. That is a data, and this is a method. So in terms of object-oriented programming language, that's the way it's going to be. So result of this, without spending too much time, result of this, you get something like this. This is like an electric circuit diagram. Each one of these little boxes are the modules at the lowest level. And the module we define is very specific. The module we define is a row of the design matrix. The result of that is you get a diagram like this, we call a flow diagram, just like an electric circuit diagram, okay? Just like instead of capacitor, resistor, we have these modules. It turns out that this is generated automatically once you do XML design. With a click of a button, you get this whole thing. Then the only thing the programmer does is stick in the modules. In fact, programmer who works on this module, it's all as very simple modules because this is a row of design matrix. This person can be located in India, this person can be in Boston, and so on and so forth. And all you have to do is stick them in there, just like you pop in resistors or capacitors, and then you have a software. I teach this to, right now I teach graduate students in my XML design class. And it turns out that one of the students is a PhD from MIT who worked for Xerox for about 15 years. He came back for a master's degree called Systems Design and Management Program. And I have another student who has also equally long experience in software design at Xerox. And they tell me that the way we did this took only 20% or less of the time it normally takes at Xerox, the software we developed. They know the software very well because they play with it, and then they work with the people who are doing this. And in the case of hardware design, machine design, I was talking to president of SVG the other day, Bill Hightower. He says, now he really thinks we can cut down the time it takes to develop new machines by factor of 2. What it used to take 30-some months, you can do it in 18 months or so. So systematic thinking, having a very rigorous criterion for good design, enables us to do this. The purpose of talking about this is the fact that not only I want to tell you a little bit about my own work, but the fact that we started out with very basic research, asking the very simple question of what constitutes a good design. And then having done all of that, now we can apply it to software design. This is technology innovation, software design, hardware design, or what have you. So I think the mechanical engineering departments must weave all of these information technology in teaching our students. Otherwise, I don't really think they can become leaders. Without having background in information technology area, I don't think our mechanical engineering students can ever become leaders. They can continue to do traditional mechanical engineers' work, but if our goal is to produce people who can become leaders, they have to have understanding in this very important area. And having done some of this kind of work and having seen what my colleagues I have amazing colleagues. That's really, it's an understatement in many ways. Many of colleagues, as you'll hear today and tomorrow, are really doing very, very amazing things. And I'm convinced that the kind of things that we can do in mechanical engineering will contribute to the future of information era. And that's, with that, I guess I'll stop, and that gives, I guess, right on time. Eh? Okay, thank you very much.
Actually, we have time for a question or two.
Yes?
You mentioned, for example, well, you're saying that MIT is taking the lead in IT, or
I didn't say that.
Excuse me, no, I mean, what I meant to say.
I said we're doing a lot in it, but I didn't say we are taking lead.
That was the wrong statement.
Yeah.
What I meant to say is that this conference is in some sense going to influence other mechanical engineering departments throughout the country, perhaps, or there might be an offshoot of that. And you mentioned, for example, optics as an area, and that's not necessarily typically something that all ME departments take as a lead area. Do you see that as developing in the future? Do you think that is that typically going to happen in physics departments or electrical engineering departments? Or?
Physics department more or less gave up optics, right? Because that's not how you get Nobel Prize, right? So you get out of that. And until we start looking into information technology area, we really didn't think optics was that important for us. We hired somebody on a part-time basis to teach optics, but there was half-hearted the sort of attempt to offer something. But then it's very clear, once you get into information technology area, you cannot deal with small things. You cannot deal with information transmission, communication, measurement, all those things without optics technology. When you're trying to deal with atomic level tolerances, there's no other way. And so I think it's a very important topic. In fact, I'm very pleased that we are so strong in the optics area. It's amazing what they can do.
Donald Dapple from UCI. I have a question. You mentioned about adding the classes related to IT to the curriculum in mechanical engineering. I'm sure that at MIT as well as other departments, we have a curriculum. Which classes, how do you incorporate that into the curriculum? Do you put them as electives, or which ones are you sacrificing to include?
Yeah, that's a long answer to that. And then Harry Asada, I guess, may talk about this. There are a couple of things. One is we created undergraduate level, the elective subject, undergraduate and graduate level. Seth Lloyd's teaching in the area of information. What's the probability? What's the title?
Information and probability.
Yeah, and then we have in the process of creating what Harry Asada calls gateway subjects. So our students can take certain set of first level graduate subjects, and then they can move right into advanced graduate subjects in electrical engineering and computer science without having to take all the other prerequisites. So we are trying to convince our colleagues in electrical engineering that our PhD students in mechanical engineering ought to be able to get a master's degree in electrical engineering as well while they're working on PhD. But we are still in the discussion stage. So there are lots of those things are happening. And the fact that we are emphasizing information means that lots of other subjects we teach will bring some of these things in design subjects and other subjects. We teach them about what we mean by information and so on and so forth. So both independent subjects as well as incorporating some of these ideas into existing subjects.
Actually, in the interest of time, I think perhaps we should get going. There will be education, of which Professor Su will be a member. And during those panels, we're going to hope to have a very general discussion. So if you have questions, some of them might be properly saved for those panels. Our next speaker is Tuscan Torossian. He is the CEO and chairman of the board of Silicon Valley Group. We're very lucky to have him here because he flew out yesterday to come here. He's flying back to California this afternoon, and he's flying back here on Sunday. And this morning, in talking with him about the ups and downs of the semiconductor industry, he's the only person in the last 5 years who's made the life of an MIT professor sound calm. So, Anne, Popkin is more than anybody here, responsible for bringing mechanical engineering techniques into making the information revolution happen. So, Carpenter Torossian.
I think the question that was asked Professor Su about how do you get mechanical engineering, what do you teach here to really make it relevant, what courses you take out, and what is a, I'm sure that a lot of you over here can spend a week discussing that because it's very, very important and very relevant. Can you hear me? If I stand back here, can you hear me? I just want to know how sensitive it is. Can you hear me now? Yes? Thank you. Okay, let me just, I'm a mechanical engineer by training, and to repeat what Professor Su said, that the optics that I learned here was a freshman physics course, was the first 2 weeks of the freshman physics course, and a book was by Professor Sears, which was written in the 50s, so that gives you an idea how old I am. And frankly, it's still relevant. So the message is, what the professors, what good universities, Berkeley, MIT, Stanford, all the good universities in the country, what you have to teach is some very, very basic fundamentals, and then teach people how to learn and adapt themselves to the changing environment. If you do two things, just teach fundamentals and teach people how to learn, which I think MIT and Berkeley and others do very well, and then that's what you really have to do, because the rest of the time, you don't know what's going to happen. When I came to school here, when I was in high school, when I filled the application at MIT, they said, what do you want to learn? And I just said mechanical engineering. Somebody said, why? Because I like cars. And that was the reason I chose mechanical engineering. I had to put something in there, because they said, what course do you want to go? And then I came here. And when I came here, believe it or not, they were not teaching anything about cars. The professor, Heschel Schwartz, was an emeritus professor, but they weren't teaching courses in cars for 10 years. What they were teaching is jet engines, because that was the era when, so you have to always adapt. Another thing I want to impart to you is that in physics or mechanical engineering or whatever you teach, you know, what I always say that you really have to teach the basic things with freshmen and sophomore, and then junior and senior, you amplify a little bit, and you spend 7, 8 years getting a PhD. All you do is learn that F equals MA, but when you get a PhD, you learn that F equals MA most of the time until you reach the realm of quantum mechanics. And that's all you do. You don't really, and that's what you apply in business. When I first left here, I was hired by Hewlett-Packard. Hewlett-Packard at that time was primarily run by electrical engineers. Bill Hewlett and Dave Packard are electrical engineers. And by the way, Bill Hewlett is a graduate of MIT. And I know that a lot of people think they associate them with Stanford because they basically have given more money to Stanford than Stanford. But they're really, Bill is a graduate of MIT. And at that time, I was the only mechanical engineer that was hired professionally, and the electronics industry at that time was moving from big boxes with tubes into transistors. And I'm sure some of you realize when you go from a big box with transistors, lots of heat, and go to transistors, small boxes, miniaturized. The biggest problem in those days, transistors were germanium and silicon, very, very sensitive to temperature. You know, if you went over 150 degrees centigrade, in fact, if you really went much over 120 degrees centigrade, a lot of these circuits did not work at all. So biggest problem was making these circuits work. So they asked me about it, and I used some very simple principles of mechanical engineering, frankly, a lot of estimates, and I just came up with some formulas which I said, well, you have to use. And they took these little documents and made a little manual about if you have a box this big, you can put so much power into it, and some basic principles how you can cool power transistors, as you know. I did simple things like, you know, put grease under the transistor, which made the conduction better, and put a little mass at the bottom, or put a little heat dissipator, and they thought I was a magician, you know. I mean, the point is, I showed them that I made a formula that temperature is voltage, and the heat transfer is current, and resistance is 1/K, and everybody thought I was a magician, you know. They understood electrical circuits. The point is, the basic principles that what you learn is really what you really apply in life. I want to share with you some of the thoughts and what we do here at Silicon Valley, and how mechanical engineering is really very, very relevant to the information age. Next slide, please. Well, I want to spend some time here, and I also want to say very little about bioengineering. As you know, when I was going to school here, Professor Mann was here. He was working with the University of the Mass General, working on prosthetics and limbs and things like that. At that time, we always think of, today, mechanical engineering is so essential in medicine, because we measure temperature, pressure, flow. And nowadays, before, doctors always guessed at things. You know, they kind of, that's what they call practice medicine, because they really practice on us. But today, you can actually measure things. We can actually give them temperature, pressure. We can give them, you find out a lot of this information is very, very relevant to what's going on in your body. Next slide, please. This is, by the way, you don't have to take any notes. All you have to do is give your email address to Professor Sunny or Lloyd, and then we'll email all this. These are all on a computer. We can email them to you, or we can make copies of the overheads. So, in the old days, as you know, we really had gears and mechanical engineering, and what we call the multiplier for the brawn. Mechanical engineers basically made leverage, give leverage so that human beings can lift large weights. And nowadays, of course, mechanical engineering is empowering what we call the brain. Next one, please. As Professor Lloyd said, mechanical engineering is at the core of what information technology today. You cannot make semiconductors without mechanical engineering, frankly. I'm not going to be that selfish. There are some chemical engineering, and there's some material science, and there are some other disciplines. But fundamentally, to get down to the small geometries and to really, really measure a lot of these things, the mechanical engineering is at the heart of it. And our company, frankly, I will say this, you cannot make Pentiums, which is since 1994. Every Pentium, most of the Pentiums are built on our machine, and every generation of Pentiums that is advanced from 120 megahertz up to 1 gigahertz now, the only way you can get that is to make the lines thinner and put more transistors on it, and we at SVG are the enablers for that basic technology that was developed, and I'll show you how that works. So we are extremely important for the whole internet and information technology. Next slide, please. For those of you who have not followed the semiconductor industry, basically, you know, you take a big ingot that, in fact, I have seen at MIT a big place where they used to grow ingots here, and they gave it to IBM. You take that ingot, you sew it first, the mechanical engineering problem, then you take, you basically put photoresist, you spray photoresist on it, which is another mechanical engineering problem. How do you spray something that's kind of viscous smoothly? You got to get accuracies of plus or minus 20 angstroms. That's what you have to really do on this, so on a 1 micron thickness. So what we used to do in the old days, we used to really charge a huge capacitor and suddenly put it on the motor, and the motor really spun it very fast so that you can really get acceleration very fast, so that you can really get a good flow. Then, of course, after that, you have project the image, which is another mechanical engineering what we make. You have to project the real tiny transistors. In the old days, it used to be 5 microns. Now it's 0.18 micron is the technology today in production. And then you develop it, and of course, then you etch it, you put some other stuff in it. There's another mechanical engineering. We make furnaces where we basically, it's a heater, and you basically put some gases in it, and you have to make sure that there are no stagnant flow. You have to really flow it properly, another mechanical engineering phenomena. So really make sure that you don't have any particles and you have smooth flow, another area of mechanical engineering. So I really think mechanical engineering goes into all of it. Next one, please. Lithography, of course, is basically the most difficult and the most important part of the making semiconductors. That's the ability to put the finest image on the wafer. And if you can't do that, whether you etch it, whatever you etch, whatever you develop, whatever you do is nothing. That's the basic enabler that gets to thinner and thinner lines. And believe it or not, optics, fundamental geometric optics that's taught in 2 weeks or 3 weeks, that's all we use year after year for the last 30 years. So, you know, whatever you learn in 2 weeks, maybe you should amplify it a little bit, some applications so that people can get better at it. And like Professor Su said, the physics department, you know, I think that's very elementary. But, you know, when you really start using it, really making machines with it, you find out that it's not that elementary. Things get very, very difficult. And next one, please. This is a sketch of a typical machine. You know, it is amazing sometimes that the damn thing works at all. Frankly, it's just so accurate and so precise. Just to give an idea, we actually do print 0.1 micron. And the accuracies are within 0.01 microns. So you have to make machines that measure 0.01 microns because you cannot buy these things. And these machines, these carriages have to accelerate. Just to give an idea, these things run about 100 wafers per hour. So it's about 1.5 wafers per minute. So in 60 seconds, we have to take a wafer, put it in, take it out, put it in, and then put about 50 or so basically dies on it. Take it out, all accurately, and you have to do this. So these are very, very fast and very accurate. Everybody can do things slowly, and you know. But when you start, you basically have to hit a machine and you stop the vibration and do it. I used to make disk drives before at Hewlett-Packard, but disk drives compared to this, we used to always argue about, you know, how fast you can accelerate something and stop it. We find out that when you accelerate something, that's okay, you can get there, but then it vibrates. So how do you stop the vibration before you can start reading or printing? And I think most people realize that in disk drives, the settling time sometimes is much longer than the access time. And I think in these cases, we have to bring it in, align it accurately, which is wafer to wafer, layer to layer. You have to do 26 layers on top of each other, and align it within 0.01 microns, and do it. And just you can understand what we're talking about, you know. The difference between physicists and mechanical engineers is that physicists talk about it, mechanical engineers have to do it. That's for Professor Lloyd. These things really have to go, you know. You know, I was at a meeting the other day, and I pointed out to some people that when we went to the moon in 1969, the computers that we used to go to the moon were so elementary, I mean, compared to today's PCs in terms of power. And those astronauts literally, what I call, they had the ass test, you know, they really literally had to fly those things with their feel. You know, you couldn't see it very much, as you know. And it's amazing that we were able to do that at the time we did it, when you think about it. The amount of computer power we have today compared to what we had in the 60s is just, well, you know, in 1965 was the IBM 360 was invented. So 69, there's not much technology, and the PCs didn't come in until about 1981, 82. And as you know, they were 8-bit machines, and they were very, very slow, elementary. So next one, please. This is kind of an actual picture of that schematic diagram of we use some robots, and frankly, these materials have to be very light, very stiff, and damped, very accurate. And so we do this actually. Believe it or not, these machines do exist in production. Next one. And they are making wafers every day, and that's what enables the whole information technology. There's another picture what a wafer is. These are 8-inch wafers, and we're going to 12-inch wafers. Of course, then you can see handling, making a 12-inch wafer and making a smooth photoresist on it at 10 to 15 angstrom accuracy, you can see it gets much more difficult. And we are working very closely, by the way, with MIT, because the knowledge today is, we don't have all the knowledge, and we really try to tap on the knowledge at the university so that we can get the best technology available. In fact, I'll show you some slides later as to why it's so important for industry to work with a university today, whether it's MIT or Berkeley, just because the information is transferring so fast today that the days when researchers made something, wrote some papers, and 10, 15, 20 years later it went into industry by osmosis or diffusion, whatever it is no longer valid. You really have to get instant, latest technology, and as well as the professors. Professors need to work with the industry to find out the real applications. And Nam tells me many times when he comes visit us, sees the machines, he thinks of 10 ideas, and his students come in and his professors, because what we do a lot of times, you know, we're trying to accomplish something and we're in a foxhole. We don't see sometimes what's going on. And one professor or the student comes in, he sees all these things that we're doing wrong, or we can do better. That's another, I think, interaction is necessary between industry and university today. Another one, please. Another picture of the robotics that we use. And another one. We use optical polishing to 1/300th of a wave. And we used to use old, what I call German opticians, because we don't even make opticians in America anymore. To really polish these things, to measure it, polish. But now, believe it or not, in California, Richmond, there's a company called Tinsley, which we purchased. They developed basically a method, computer controlled, where they are measuring while they are polishing with the feedback. And we can do spheric as well as aspheric lenses. And this was really done, and that's probably the best place in the world where we can actually do aspheric lenses very accurately by computer-controlled optical polishing. Next one, please. This is a picture about how when we rotate what I call the wafer and we put photoresist on it, you can see all the flows and the pressures that occur when you really want to make this thing very, very, very thin. The reason that you have to control within 10 to 15 angstroms is because because every chip is about maybe nowadays between 1 centimeter square or 2 centimeters, and you have to make sure that every part of that wafer has a uniform flow. Otherwise, you don't get the speed and you don't get what I call CD control, critical dimension control accurately if you don't have the thickness right, and therefore you don't get good yield. And yield is the name of the game in this business. Next one, please. Well, mechanical engineers, you know, we're also very, very much interested in sensors, actuators, and of course, some of you are very close in the controlling. As you know, controls about 15 years ago, control was very, very, very important. Now, of course, it's going more into biotechnology as well as a lot of numeric IT technology, but extremely important. And all these technologies, we use planarization, which is the chemical mechanical polishing. It really is extremely important today. It's a very dirty process. It's really polishing and then it's grinding, but except you have to do it very accurately because if you don't do it right, you basically eat into the chips and you have very low yield. It's another mechanical engineering process. Go ahead, please. That gives you, this picture probably gives you what we're talking about. You know, as most of you know, 1 centimeter is 10,000 microns, and your hair is about, 300 microns. So we do, just to get an idea, 1,000th of a hair, 0.18 now, it's less than that even, maybe 1/3,000th of a hair. So it's really very, very small dimensions we're dealing with, and we have to measure it and fabricate it and control it, and of course keep the dust out. Next one, please. This is a very, this electromagnetic spectrum that gives you an idea. But basically, we are working today at basically the GNH lines are 436 nanometers, and the I line, which was used until about 5 years ago, 365 nanometers. We are using 248 nanometers now, and now we're going to 193. And of course, next is 157 nanometers. That's basically the source of light. Next one, please. As I said, our company is the leading producer of lithography. We really do deep UV beyond UV, lower than 4,000, shorter than 4,000 angstroms, or 400 nanometers, which is visible light. Then we're going with 193. Next is 157, and then EUV. And these are all optics until about 2006 or 2008. We're still going to be geometric optics. People want to know when the technology is going to stop. We're still using optics. EUV can start considering whether we're going beyond optics. And there's a lot of discussion now in universities whether we should go to the next. It's going to be on human cells or on tissue instead of silicon. But right now, I think for the next 10 years, we'll be using silicon and optical techniques. Next one, please. And I think what I talked about is what mechanical engineers to opticals, basically to information technology. And I think I want to spend some time telling you what information technology has done to us in mechanical engineering. And it helps us in product design, in manufacturing, and they call Mechatronics. I'm sure some of you here teach Mechatronics in your school. Next one, please. As you know, if Da Vinci had computers, and CAD systems, as you can see that the design that his innovation was not any worse than we did, except he didn't have the tools. So the tools that we have today, like the axiomatic design that we use, really, really speed up and really make mechanical engineering life very easy. For example, when I was designing things, we used to make parts that fit together. Sometimes we made mistakes and parts didn't fit. Very simple. The holes were at the wrong place. Today, you can actually do on CAD, you can actually simulate it, make sure they're in the right place, and before you do it. And equally, by the way, most of you work with software. Software has the same incompatibilities as the hardware does. And most of the time, software guys get away with it, get away with selling things that are not finished. Unfortunately, in hardware, you can't. And your computer suddenly freezes. You put a new program in it, new application program, the damn thing doesn't work. So what happens? Because there's a software incompatibility with it, but software guys don't admit that. They said, it's a user problem. That's why they charge you 15% a year to just maintain it. But those things can be done by axiomatic design. It really looks at the axiomatic design. Really, nothing but a replacement of a good engineer. If you have a good engineer who really thinks clearly, you probably use axiomatic design mentally. But axiomatic design makes a good engineer a great engineer by showing systematically what you have to do and what avoids potential problems and conflicts. Next one, please. Like I said, we have now we are using PCs. We have computer networks now. We're using the internet now for really sharing data and sharing knowledge through. We used to use picture tail and other things by the television. Didn't work. Now we have to use the internet. Actually, you can share data and online instead of waiting for a long time. So actually, mechanical engineers now use that. Next one, please. And I think this is a very interesting chart, and I think this is something that all of you in the academia really should really pay attention. This is an important. It shows here that in the 1 megabyte, the red one is in the 1 megabyte. You see how long it took? It took about almost 186, almost 4 or 5 years for it to mature to its maturity with the number of units. It's on the left, on the abscissa is on the ordinate is the millions of units, on the abscissa is the years. It took 4 or 5 years for it to mature, and then it took almost 10 years to decay. But the next generation, it took faster ramp, and the next generation is faster ramp even that. And right now, we are really doing, we're 64 megabytes going, right now it's dying, but look how fast that grew, and now we're going 256 megabit, and it's really growing faster. What the message really here is, and I have another chart that will show you, that's why I think it's extremely important for universities and industry to work together. And then the next chart, please. This is a chart that was recently published, I think, in Business Week. You can argue with the numbers, But fundamentally, it says that it took, on the left side, on the ordinate, you see the percentage of US population penetrated, and the abscissa is the number of years since the product invented. You can argue whether the telephone or the automobile or the electric was invented. You can change it by 10 years here and there. But the point is, it took almost, let's say, 50 years to 60 years for the automotive to penetrate 25% of the population. And if you look at the left, the farthest left chart, it took less than 6 years or 5 years for the internet to penetrate 25% of the US population. And the message really here is that things are moving a lot faster. And I think it's extremely, extremely important for us in industry and academia to work together and vice versa, because we don't have the knowledge. A lot of us don't have, and you have a lot of new ideas and new knowledge. And I think we give you a lot of application capability. We give something to sink your teeth into. And I really think that's extremely important for us to establish the collaborative effort. And we have here, next one, please. In manufacturing, supply lines, and as you know, let me just give you an example that not even in our industry. My brother-in-law is a vice president of a garment industry. You know, so what's relevant about garment industry to our business? It used to be Sears and Walmart and all these guys, they ordered something and they basically got the clothes and they put them in a warehouse, and they built huge warehouses, they distributed these things into their various stores, and and then they basically sold them. Today, what happens is these huge department stores like Walmart or Sears or any others literally they have thousands of distributors and suppliers, and they tell them to tag this model machine, whatever clothes they're making. And you know, in the clothing business, believe it or not, clothing is just as perishable as computers. I mean, if you don't sell something for the spring, they're working, right now they're working on the next fall fashion. And if the fashion doesn't sell, it's perishable. That's why you get them into all these outlet stores, and they really, so they have to get this machine, they have to accept the design, they have to manufacture it, they make it to various sizes, put the tags, and send it directly to the store. And in the store, you have all these new computers now. They even tell you exactly where it came from, and every day they look at how much they are selling, and within 2-3 days, if they didn't sell that much, they take it and they send it back. Or they sell it a lot, it automatically reorder it. What I'm saying is, even as mundane an industry as the clothing industry, the whole information and the speed of operation is happening. So we in mechanical engineering, we in the manufacturing, we have to do the same thing. We really improve our process lines, process systems, and the days when you designed a part and you went to the machine shop, 3 months later you got it and it was wrong, you got it back again. It doesn't do that anymore. You really have to do things accurately and very, very fast. Next one, please. Another area that mechanical engineering, reliability. You cannot do things. When I came to this industry 15 years ago, our machines probably worked about 150, 1 week. 1 week is 160 some odd hours, and the way they looked at it, the machine lasted a week without anybody touching it. They were okay. But when you are going into a lights out, what I call automated factories, and you have 500 steps to make a semiconductor, and you have a lot of machines, different machines, complex machines, different processes, and you want a lights out factory without people, because people contaminate the circuit, you have to have reliable machines that have to work. And uptime suddenly has to go into thousands, not hundreds of hours. These complex machines have to work reliably. And what better thing to do than mechanical engineering to really make these things, all these dynamics things, really, really reliable. All these probabilistic theories, and you have to design things properly. It's extremely important. You cannot get automation without reliability. As you know, the jet engine, I mean, if you had an old airplane engine, you know, every few hundred hours you have to really fix it. Jet engines last 12,000, 15,000 hours between overhauls. And you know how very seldom you hear a jet engine fail in an airplane. You just take it for granted today because of mechanical engineers. Those are the guys who were teaching at MIT when I came here. The next one, please. Well, I think that all these diagnostic systems internally to really self-correction, right now we're designing machines that instead of sending all these technicians all over the world, we can actually diagnose them remotely and start really get the information and then immediately feed back to the manufacturing floor. So these are all systems that the new information age is helping mechanical engineers get systems fast. In the old days, you have to bring the part in, you have to spend a whole job on analyzing it. Next one, please. But today, you have to do it faster. And I think there's a professor, too, I'm sure, that teaches mechatronics, the whole system of working together of traditional systems and old systems. Next one, please. In any case, in the 70s, we had the servo technologies. Then we had the 80s, the IT technology. Now I think we have the entire confluence of all the other systems and actually feedback systems and using the technology to really get our job better. So that's what you have to really teach. Next one, please. That's a complex chart, basically. I'm sure most of you can draw your own chart, or you can use this one when I send the email to you, what the general field of mechatronics, which is really a lot of the disciplines combined into one, what we call mechatronics. Next one. Just to give you one slide on, I don't want to slide the people who do in bioengineering. I mean, I really feel you can spend a lot of time deciding about, that's the next field of bioengineering, and I really think I'm very pleased that MIT under Professor Sue's leadership and Neil Papalardo's chairmanship adopted the concept of creating a very strong bioengineering field at MIT, because I really feel that that's the next, basically, horizon for us to conquer as to how we can get this complex body that we have. You know, I always say God was a very good engineer, because every time you look at the body, the way it works, it's amazing. So I think if we understand it and measure it with a lot of mechanical engineering principles and use some of that to really influence it and correct it, we can probably don't have to practice medicine, we can actually do medicine. So basically, next one. So basically, these are a lot of examples of, you know, we always think of sport engineering and other biotechnology as bioengineering, but basically mechanical engineering do just pressure, temperature, flow, and all these things we have to use. That's it. Thank you. You can take that slide out. So I just want to let you know that mechanical engineering is at the heart of things, and I think that the job here, again, is to teach them very, very basic principles and teach people how to learn as they adapt themselves. You know, like I said, I was the only mechanical engineer at HP that was accepted, but now, of course, things are a lot different, and they realize that mechanical engineering has a huge contribution to the IT industry. Okay, thank you.
No questions? Thank you. Let's thank our speaker as he goes. Good morning again. Thank you very much.